Okay, welcome everyone. So this is module 6.4. I talk about a whole bunch of little different things, best practices, parameter files, basic parameter scan, and I got parameter files in there twice. I might overlap a little bit with some of the stuff that Lorenzo and maybe even Giuliano covered. Let me know if I start on something that we've already gone over enough. If my Zoom freezes, just let me know when I unfreeze and I'll back up a little bit and try to cover whatever I dropped off on. So we're going to talk about, first of all, some hints and tricks for simulating HoppyCell, some best practices and how to do parameter files, parameter scan, and then this slide deck has a number of other sets of slides if you're interested in looking at them, writing in files in general, writing to a log file where you want to keep putting results from simulations into the same output file, how to do replicate runs, which I think Lorenzo covered a little bit. And there's some slides about parameter sensitivity if anyone's interested, but I don't think I'll get to these last four things. So we're now here at 6.4 module on Saturday. And we'll start off with some quick tidbits about running CompuCell simulations. It doesn't matter too much if you're running it locally on your own machine or in Jupyter Notebook or some other way. These comments should help in all cases. The first little trick is you should always do one extra step. When you're writing your steppables, you often tell it to run every 10 steps. You might be saving screenshots every 100 Monte Carlo steps. But just to make sure at the end of your simulation that you get that one last trigger of all of your steppables, just run a separate, one extra Monte Carlo step. That'll make sure that everything actually gets done at the end. In addition, it's usually a good idea to increase your neighbor order. The default is 1. It's usually better to use a little bit higher neighbor order. You'll pin your simulation less to the lattice, that is, things won't be quite as square. The drawback of higher neighbor order is it'll slow things down a little bit. CompuCell can use multiple CPUs. In your standard XML file, there's an option to increase the number of processors. CPUs, threads, whatever the particular platform wants to call those things. But if you do increase the number of processors, you should check that it actually makes a difference. A lot of times you'll increase your CPU usage, but the simulation won't run faster. And that's because multiple CPUs is pretty complicated in its implementation in CompuCell. And it doesn't always result in faster simulation. Easy way to check that is perhaps you've noticed at the end of every CompuCell run in the console, there's this little timing report. If you're making movies, this report is up above all the text about the movies, all the debug information about the movies. So you might have to scroll up to find it. But in any case, you can go up and find how long the simulation ran. If you change the number of CPUs, you should check and see if the runtime actually changed or not. Or if it changed enough to be worthwhile. If it changes 2 or 3%, it's really not worth running multiple CPUs. You do have to be a little bit careful. Different platforms calculate this number differently. On Windows, this is essentially the maximum time used by any CPU. And I believe in Linux, this number would be the sum of the CPU times across all CPUs you used. So you have to know a little bit about how that number is calculated to see if increasing CPUs makes any difference. If you really want to double check, you can go to your screenshots, if you're saving screenshots, and just look at the timestamp on your first screenshot, the timestamp on your last screenshot. And that gives you, that's a robust measure of how long simulation took in the units that really matter to you, which is how long you had to wait and stare at the screen while it was thinking. You really don't care how much CPU you're using. You really care about how long you had to sit there and stare at it as it was running. So you can explore using more CPUs. Sometimes it helps, sometimes it doesn't. Another thing to consider is how often to run your steppables. Some things in steppables are very slow, like visit all pixels or visit all cells or visit all cells and then visit all cell neighbors. Those are slow processes, and that's all done in Python, and so or largely done in Python. So it may slow your simulation down quite a bit. So you might want to change. So in the timing report, it'll tell you how much time you spent in each one of your steppables. This particular simulation only had one steppable, and it's using 18% of the CPU. You really don't want your steppables using up more than 10 or 20%. And if you got a really slow steppable, it could easily be 80 or 90%. So you want to fine tune your steppables to try to get this number down a little bit. You really can't do a whole lot about the compiled C++ time, other than doing things like removing surface constraint and other very fundamental things that sometimes take a lot of time to calculate. So if you do change how often you call a steppable, you have to remember that whatever's in the steppable doesn't get done as often. So if you were doing growth rate of 0.1 pixel every MCS, and you're going to change that steppable to run every 10th MCS, and you have to remember to increase that growth rate to 1 because it's only being done 1/10 as often. So you can control steppable frequencies in the project pipe file where you register your steppable. You can assign a frequency. In the class definition itself, in your Python steppables file, you can define a frequency. A more common way of doing it is just to set this to 1, and in your Python, use commands like this. Use modulo arithmetic to decide, well, I only want to do this particular chunk of code every 10 Monte Carlo steps. And this one I only want to do every 100 Monte Carlo steps. And you can also tell it not to do step 0. That way you're not doing some calculation at startup that perhaps you can't do yet because the simulation isn't quite ready yet. So the next thing is, early on, you should make a decision about what your basic units are. You can always change your definitions later, but you should start off with a note somewhere saying, I've decided that 1 voxel is 1 micron across, and I've decided that 1 MCS is 1 minute. Even if you don't use that in code anywhere, you should put it in a comment someplace, just so that you understand what your thinking is. Now, as I say, you can change that later, and you may change that later, but to start with, it should be somewhere. There's a couple of speed limits in CompuCell. One is the maximum speed that you can move a cell. And another common speed limit or common time scale is if you have cell cycle and cell division, what's the biological time scale for that? So if your cell cycle time is 12 hours, takes 12 hours for a cell divide, 1,000 MCS per cell cycle is a reasonable starting place. It gives you lots of time for the cell to grow and relax. Then from those two, you can calculate that 1 MCS is 43 seconds. And so again, you can put a note in your file somewhere that, okay, I'm working based on my cell cycle time and the fact that I want 1,000 MCS per cell cycle, 43 seconds per. So write that down somewhere. One way to do it is just to go into your Python steppable file and make a multi-line comment and just write those things down. You can't use them for anything, but at least you have it written down someplace. A little trick, you can actually put a multi-line comment into a variable. And the reason you might want to do that is at the end of the simulation, you might want to print that model definition, this set of parameters. Maybe you're printing it to a log file or somewhere else. Okay, so just some quick hints, some things to think about when you're trying to get your simulation to run and trying to get it to run fast. The next part is best practices and ways of trying to keep things organized. Lorenzo talked about it a little bit, trying to get all your multiple simulations basically in the same Python file. But there's other ways of doing it. A common way is to use a system like GitHub or SourceForge. In fact, CompuCell uses SourceForge. The advantages are the programmers already know how to use it. It has very robust versioning. It reliably retains previous versions of things, and it's an excellent way to share code with others. The disadvantages is that non-programmers don't usually use it, and there's a pretty significant learning curve to really use GitHub or SourceForge correctly. And of course, if you don't have internet access, you lose access to those files unless you have a local copy of it. A second way of doing it is Google Drive or Dropbox or some other online sharing, something not quite as robust as GitHub, for example. The advantage is it's easy. It does typically keep previous versions of a file, and it's easy to share with others. The disadvantages, it can be a challenge to use the files on the local hard drive. Can you actually mount Google Drive or Dropbox locally? Which actually you can do, but it can be tricky. It does, of course, require internet access. And especially if you're using the Google Drive to save things like screenshots, you could easily run up into the 5 GB free limit of Google Drive and have to start paying for your online storage. Kind of a quick and easy way for non-programmer, non-hardcore programmers is just make sure you keep local versions. It has the advantage of being very easy and straightforward. You don't need any other tools. The disadvantage is it's easy, very little protection against file loss, and a little ability to trace the evolution of your project. It's easy to develop broken code and not be able to go back a previous version that worked, and it's not easy to share with others. But you can do kind of a hybrid version in which you just try to be careful about saving copies of your simulation as you're building it. So you basically create frequent zip files that just freezes a snapshot of your project at a particular time. Its advantages, it's fairly easy to do. If you do it from the workspace folder, you'll get whatever was in the workspace folder. The disadvantage, of course, is you have to remember to actually do it. And if you don't do it, you don't have any backup copies. When you go to the workspace, I'm not sure if anybody's shown the workspace. I assume somebody has shown it before. But CC3D.
No, I don't think they have, Jim. I think that would be a good thing to show.
Okay, so by default, CompuSol will write results to a directory called CC3 Workspace, which is usually right below your home directory. And every time you do a simulation in CompuSol, it'll create a new file in this workspace directory. The name of the file will be the name of your project, then with a long timestamp added onto it. So this was August 3rd, 2024 at 12:33:54 in the afternoon. And then there's a little hash character just to make sure that every single one of these folder names is unique. Inside of that folder are all of your folders, your simulation folder and your CC3D file. If you're saving screenshots in the simulation, there's a folder with all that in it. And in the simulation file is all of your steppable files and parameters, anything else that you have in everything that's in your CompuSol project. So every time you hit run in Player, it'll generate this. If you get a good run, it's great to just go into this folder, double click on it, make it a zip, get it out of the workspace, because periodically you probably want to go in and clean out your workspace. But then drag that zip folder into your working project file and say, okay, now I have a timestamp of here's all the code that was run, all the parameters, all the steppables, some of the results, screenshot images and things like that. So this is a quick and dirty way of maintaining a backlog of what you've done and as you progress through developing your code. Every time you get something that seems like, okay, that was a big step forward, well, go into the workspace file and make a zip of it and drag it back and save it. The next thing is you really should have a biological description. James probably talked a little bit about this early on in the class. We really should keep a running document that says biologically what it is you're trying to do. And that should include a very simple thing like, what is the domain? This is cancer. This is wound healing. What is the overall domain of the project? A little list of the entities, physical entities like cell types and diffusion molecules. A list of the processes, diffusion, cell growth, cell division, cell death. And it's great to link these two together. So you can say, I have a cell type of hepatocyte, and the only process it has is cell death. And try to keep track of that. And then a simple image is immensely useful especially when you're starting up a new project. This was a image that Teru Matsuura sent to me a year and a half or something ago. Of this was a fertilized egg implantation in the uterus, and that's all he gave me, and that was all I really needed to start building the CompuSol model. Didn't have to be super complicated, didn't have to have a lot of details, but it tells me what all the cell types are and the basic processes going on. So a drawing like this is always super handy. You can probably find a really good Google image for wound healing or epithelial cancer or whatever your project happens to be. Grab that image and it'll help you guide your thinking. You can save the image in your project folder. and it should propagate every time you do a simulation, every time you make a copy of that folder, etc., so that that image is always with you. So the biological description can just be a Word document, or whatever your favorite editor is. If you keep it in the top level folder, it'll move with the rest of your project. It can be also kept as a plain text file as part of the CC3D project directly, and I'll show you some examples of doing it that way. Of course, the problem with doing a text file is you can't do images and things like that. So it's nice to have that Word document where you can keep pictures and better formatted descriptions of what's happening. The Word document can also be used for every time you make a landmark improvement in the simulation. You can go into that Word document and say, here's the name to the zip file that I saved out of the workspace folder, and this is what it accomplished, and here's 2 or 3 screenshots. And that's a real easy way of now being able to go back to, well, what was the project looking like 2 weeks ago, as opposed to what it looks like today. So it's a good project, a good idea to keep track of things, and a Word document is a reasonable way of doing it. So now we'll talk a bit about parameters. So tracking parameters within a computational project is a challenge. The worst case is that your biological parameters are actually not defined anywhere in the model. Your things like cell volumes are defined in pixels, and your diffusion coefficient is in pixels per Monte Carlo step. And so you really don't have any link back to the biological parameters. The next worst case is that the biological parameters are in there, but they're not done. They're scattered all over the code. You don't specify what the units are. And you start to have problems with, well, you make a change in a particular biological parameter someplace in your code, but you forgot that it occurs somewhere else in the code, and the other place doesn't get changed. Now you've really made a bug in your simulation that's going to be really hard to chase down. So the modelers should track and organize their parameters in some clearly defined way. In addition, when you're doing that, you should be able to include things like the units of the value and a reference. If you can actually point to a literature citation that says, well, hepatocytes are 15 microns wide. So you should be able to track that it's a hepatocyte. 15 is the number, and the unit is micron, and the reference is whatever your reference happens to be. So one way of doing that is just to put it into comments and commands at the top of, for instance, your steppable file. And so you go ahead and just put in a global conversion, seconds to Monte Carlo steps is some function. And days to Monte Carlo steps is some functions of seconds to Monte Carlo steps. And this definition here that a voxel is 1 micron across. Once you start doing that, you can start defining your computational parameters based on your biological parameters. So I can say, well, my biological cell width is 10 microns. Within my model, my voxel to micron conversion has been defined. So now I can calculate some feature of my model based on this biological description and my conversion factor. In this particular case, what I was doing is I was defining the width of the model based on not pixels or microns, but on the cell width of the model biologically. So I want to be able to say my model is 10 biocells wide. How that turns into a CompuCell model width depends on what my pixel to micron conversion is. And so I can calculate the proper model width in order to get exactly cell width, and that's the wrong unit. That would be cell volumes. No, that said, no, that is cell width. Width of the model, though, can be calculated from it. And I think I got my math messed up there. You can also do things like, well, you have a diffusion coefficient. Well, literature value is going to be in centimeters squared per second. You can use your pixel and your time conversion factor. So, okay, this is what the diffusion constant is in the model. So now we're going to be in units of voxels squared per second. So it's a good idea to go ahead and create a parameters file. Like I said, you put it at the top of your steppables. I kind of like it better to put it as a separate file. You can break your parameters up into your biological measurements, your scaling factors, and then your computational units. So this is in centimeters squared per second. This one's in voxels squared per Monte Carlo step. And you can write equations that let you convert from one to the other. Try to include the units for your parameters, whether it's a biological parameter or a modeling parameter. And if you have a reference, include the reference in the file. It's also great if you can do this, actually link your cells, your processes, etc., to an ontological term. And let's see if, so I clicked on that link and that opened the ontology search. And it says, so this thing is an epithelial cell of the lung. It's a very robust way of defining what your cells are in a way that someone else can understand, and allows you to make up any name you want to use in your model, as long as at some point you say, oh, what I meant by epi is this thing, and point to it somewhere. So let's do a little test. What we're going to try to do is add a parameter file to a standard CompuCell simulation. If you want to open the self-sorting base demo and try to follow along, I am going to do it as well. Let's see, let me get this open. What we're going to do is add a parameter scan to it. We'll see if this works here. So hopefully now you can see my Twedit window. So we can add a file to the simulation. Go over here to the file list, right click, add resource. And you get a list of things you can add. First thing it wants is a name. So we're going to call it parameters. I'm going to try to spell it right. Unfortunately, we have a limited number of file types. It would be really cool if this had, open a Word document or something, but you can't do that. But you can just make a regular old Python file. It'll automatically be stuck in, this file will be added into your simulation directory. There's a bug in this pop-up window. You see there's no way to get out of it, but if you grab the bottom of it and stretch it, you'll see the finish. You can assign custom file types, but Twedit has limited capability of interpreting. It's basically going to interpret everything as a text file. But in any case, I'm going to call it parameters. It's just a regular Python file. Hit finish. And now you see we get a new file here. When I save my project, this file will be saved to the project. When I reopen it, it'll still be there. Double click on it to get it open. So now I can go ahead and start adding, my global comment, cell sorting. Now when I do a save, that's now saved as a permanent part of my code. So catch up on my slides here. So you right click over here, you get the little windows, you give it a name, hit finish. If you can find it, double click on it to open that file. You can actually get it up in the file tabs. And now you start putting stuff into it. Then you give a brief description of the project goals, define your biological and modeling values, what your cell types are, how big they are, what your micron to voxel conversion are, and so forth. This example here, I tried to break things down into, so here's a chunk of code that gives the biological parameters, my model cell widths. My model is good. This is what I was trying to explain earlier. I'm going to define this model width not by microns or pixels. I'm going to say the model is supposed to be 10 cells wide. And a cell is 10 microns wide. And if I have a pixels to micron conversion, I can calculate what the proper model width is. So I can say, well, I don't want a model that's 10 cells wide. I only want it to be 5 cell wide. Or I can say I want 3 pixels per micron, which make my cells really big. Or I want 0.3 pixels per micron and make cells really small. I can change just 1 or 2 parameters and change the layout of the model. This is just that same file with more detail. So in addition, I'm defining my adhesion constants. So medium adhesion constants, medium to condensing cell adhesion constants are all defined in this file as well. Now, this is actually a parameter file. It's actually Python code. So we've gone beyond the idea of just putting in a text description of what you're trying to do. We actually have Python values in here. We have Python math in here. We can calculate the model width in pixels based on the microns to pixel conversion and the biological width of the cell in microns. So to actually use these files, at the start of any Python, you just have to import that module. So here's my parameters.py. I'm going to import parameters as P, just because I get tired of typing parameters all the time. So I'll just call it P. Notice that there's no extension on parameters. For some reason, Python import does not allow extensions. You can't say parameters.py, which is actually the name of the file. In any case, at this point, we've imported that file. Any commands that are in that file get executed at import. So for calculating model width based on cell sizes and pixel conversions, as soon as we load that file, those calculations are done. To actually use the values in that file, we just prefix the variable name in the parameters file with the P, and that P just comes. So that's how we loaded it. So here I show I had hard-coded cell targets and surface and volume constraints. And now it's getting those values instead of the hard-coded values, it's pulling them out of the parameters file. And there's a parameter in the parameter file called cell target volume. So that's how you use them. Every one of your classes in your steppable will have access to this parameters as P. If you are doing this is a Python only simulation, so there is no XML file. The nice thing about doing the Python only is all of the XML commands are in here, but they're coded as Python. So we do the same thing here. We can import as P, and I can go and pull out the model width in pixels and the model width and the model height in pixels and pull them out of the parameters file and just automatically rescale my model as I change parameters. You can also change parameters in the XML file. It's a little trickier. And if anybody really ever needs to do it, there's some help in the CompuCell documentation about how to change a value inside of the XML file. You actually do it via Python, but it's functionally the same as changing the XML. So this example, the demo has rescaling the model based on how wide the model is in pixels and how many pixels there are per micron. And as I said, so you start off with your parameters, and you can do some calculations in your parameters file to get this parameter here, which can then be imported by your other Python scripts, your steppable file in particular. And go ahead and, defining units, give it a comment, give it a reference if there is one. In this particular case, I'm just going to show reassigning the model width in the Python only XML. I think Lorenzo might have covered this, but when you start a new simulation, so this is how you get Python only. The default is the Python plus XML, but if you just click here and work through the process, you'll end up with a setup like this where you have the XML is encoded in Python, and you've got your regular Python steppable file. You don't get a registry file, but here I've done it. So a new model, Python only, and I only get these two files, and they're both Python. Okay, this cell sorting demo, I think I'll probably cheat a bit and go ahead and jump to the one that's done. But the idea is to be able to, on the fly, change not on the fly, for each simulation, easily change some of the global parameters and to enable you to run the cell sorting with different parameter sets. So cell sorting, everybody's seen cell sorting. Start off with a random mix of cells, and hopefully, if the parameters are set right, they'll sort to a core of one cell surrounded by a layer of other cells. Scaling models. Changing the scaling of model is actually kind of tricky. There's some guidance here about how you would scale adhesion values, the lambda volume and the lambda surface values. It's can get pretty tricky, and there are certainly cases where scaling a model, changing the pixel resolution actually is going to be quite difficult to do, in particular because things like adhesion J values interact with target volume lambda values, and all the parameters tend to interact. But you can do it at least partially. So this is an example of running this one simulation with different pixels per micron. So you can see as I just changed this one parameter in the parameters file, my model was 40 wide, my model was 100 wide, my model was 200 wide, but each one of these models has the same number of cells. And just some more comments about rescaling the model is tricky, but this is perhaps one reason for still being able to do it, is that a low resolution model is going to run a lot faster than a high resolution model. And when you're debugging something, you really hate to have to run for 4 hours to find out that the last print statement in your Python is a bug in it. So it's nice to be able to run the much smaller version of the model, get it to run fast, help you debug all your steppables, your output, things like that. So I am going to try to switch. Let's see. So this is the parameters example. So this has got a regular XML file, a regular Python file. We've replaced the parameters. And if I run this, so there goes cell sorting. This graph is the contact area between cells that are of different types. So it's starting to cell sort, so that's going down. Now, unless I've broken this model, it was 100 pixels wide, again, hard to see, but that's 20 cells across, give or take a little bit. Now, my model's only 10 cells across. I only changed one command. If I want to change my pixel resolution, pixels per micron, that I should still get 10 cells across, but my cells should be much bigger. Now I have to reset. Now my cells are all much bigger, but they have the same number of cells. Notice it's running much slower because now my model is 300 pixels wide. Before I think it was 100 pixels or 75 pixels or something. So this lets me make one or two simple changes in the Python, make the code run a lot different, make the code run fast, make the code run slow, get my output, see if everything is working correctly. So let's go back. You could get more complicated. If you really wanted to do this right, you might make a dictionary of parameters. And the dictionary would have one key that's your variable name. And that is actually a dictionary of dictionaries. And that variable has values, has a numerical value associated, has a unit associated with it, has a reference associated with it. That lets you make these nice little tables, easy enough to make a nice clean formatted table from a dictionary of dictionaries that has all your values in it. So exactly what your name, the variable name in your model, the numerical value, the unit, and then some reference. So this could get quite complicated. Unfortunately, Compicell doesn't have any built-in tools to help with this. Maybe we'll get them someday. Another thing that you can do with the parameter set is in your parameters file, you can just create separate sets of parameters. So here what I'm doing is I'm using a single variable to control which one of my parameters parameter sets are going to be used. So if experiment is 1, it's going to use these parameters. If I set experiment to 2, it'll use this set of parameters. And oops, I set the experiment number to a number out of range. And so it doesn't know what to do with it. So it should throw an error message and stop, not continue with undefined parameters. So this is one way of keeping multiple sets of parameters in your model making sure that, well, when I change my growth rate, I wasn't working on a different copy of my steppable files or something else. And I can also go back and change this value and rerun all my earlier simulations, all using the exact same file, the exact same parameter files, same steppable files, everything else. This could be more complicated. We could have a reference set of parameters, and what we can do in an experiment is selectively change one or two parameters in the experiment. The advantage of that is, as you can imagine, this list of parameters for an experiment could be quite large. You could have 50 values easily defined for parameters defined for an experiment. So you might want to have a base set of parameters, and when you define an experiment, you just overwrite one or two values to get a new set of parameters. A trickier extension to this would be then to take this and put it into a Python string variable. So at the end of your simulation, you could print out this directly. But there's other ways of actually getting all your parameters printed back out. You can just print your parameters dictionary at the end of your run. So the conclusion of the best practices, figure out some way of tracking your code. Very important. Even if it's as simple as just, well, at the end of every day, I'm going to make a zip file of my code today. If you're up to it and you're comfortable with GitHub, that's great. Do it as a GitHub project. Figure out some way to track your parameters, your units, your goals within the CompuCell project. At least have some description file in your top level CompuCell folder for a project. For example, so this is cell sorting based project, and I can put any file in here I want. So I can certainly add a Word document to this folder. So just to back up a little bit, go ahead and stick a Microsoft Word document in your project folder. All right, this is my folder with my CC3D file, and it contains my simulation file. You can also put it in the simulation file. But so now this will, every time I version my folder, this Word document will get dragged along with it. So best practice conclusion, track your code, keep track of your units, your parameters, your fundamental biological concepts. So that cell sorting base code is in there, is in the share. If you want to kick the tires on it and see how I did some of the stuff that's in there, feel free. Next thing I was going to talk about was parameter scans. Lorenzo talked about it briefly. I don't think he went through the steps of actually setting one up. So I am going to do that, and I'm going to use a simple cell sorting as an example. So what is a parameter scan? Parameter scan, it allows you to automatically explore a range of values for one or more variables in the model. It's an easy way to do multiple runs. So one of the things that you can easily do with a parameter scan is just run the exact same model 10 times or 100 times or however many times you want to run it, just to see how much run-to-run variability you get, since CompuCell is a stochastic simulation. It's easy to think, well, I'll just scan every parameter in the model and I'll do 10 values for each parameter. However, it's a combinatorial explosion, and you'll very quickly get to way too many simulations to run. And this should be 5 to the 10th. So to scan 10 parameters with 5 values each, that's 9.8 million simulations. So you do have to keep track of how many you're trying to do, just so you make sure it's a tractable number of scans. Depending on how much output you're creating, you can create lots and lots of output. So if you're taking screenshots every 10 Monte Carlo steps and you're running 10,000 steps, you're getting 1,000 screenshots, and you're going to do 1,000 simulations. You now have 1,000,000 screenshots in your disk structure somewhere. So you also have to worry a little bit about how much output you're generating, and are you going to run out of space sometime. Adding a parameter scan is a major code change. You can remove a parameter scans, but it's tricky and error prone. So before you do the parameter scan, make sure everything is working exactly like you want it to in your code. That if you're saving screenshots or anything like that, that it's doing it exactly right. Because it's really difficult to troubleshoot something like screenshots when you're actually doing the parameter scan. So the best way to do it is just fork your project. You've got your base project, it's doing exactly what you want. Make a copy and convert that copy into your parameter scan. So the demo that I'm going to do is just your basic cell sorting, condensing and non-condensing cells. If you're doing a parameter scan, you probably want to come up with some output metric that describes how well the simulation did, whatever it is you want to do. For cell sorting, it's fairly straightforward. You can say, well, you might say how many condensing cells are still in contact with medium. If the sorting went correctly, there shouldn't be any condensing cells in contact with medium. But in any case, before you do your parameter scan, in fact, before you put your parameter scan in, make sure you've decided on a metric and you've written code to output that metric into some place where you can recover it. So in the demo, there's a real simple metric that just calculates something and writes it to a file. So cell sorting, so kind of our key parameters. There's lots of parameters you could change in the lambda volumes and things like that, but it's mostly the adhesion values that control cell sorting. So we'll look at doing a simple parameter scan, changing some of the adhesion J values. And so cell sorting starts off with a random field, so as to make some sorted field that looks like a core surrounded by other things. This was just, before you do the parameter scan, make sure you've got some kind of an output, and there's in the full deck here, there's some how to add a steppable and tell it to write some interesting results to a file. I'm going to kind of cheat that. It's just creating a new steppable that measures a couple of things. So you've got your base simulation working, you got your outputs all right, you're writing some result to a file. It's ready to go ahead and put the parameter scan in. So make sure you fork your project. Simplest thing is just make a copy of your top level folder and rename it to be PSCAN. So it'll take me a moment to switch over to that. Or give me a moment. Stop this guy. So this is our original file. Like I said, just a very simple cell sorting. What I've added to write a result is in the finish command. It's going to iterate over all the condensing cells and just measure how much the condensing cells are in contact with, each condensing cell is in contact with medium, and sum it all up. And that's going to be basically the output of the run is this one number. When we're doing a cell sort, though, we'll also want to track the value. In any case, it opens a hard-coded file, since there are no, as far as I know, there's no compilation utility for opening a file in the projects directory. You can open it in the workspace directory. But we don't want to do that because we want just one file for all of our output. So there's a hard-coded file path. It's going to open that file for append and then write some stuff there, including our calculated metric. And it's written for append. So in our PSCAN, every time we do a run, every run will just write to the same file. Each run will put one new line in that file. But so far we don't have a PSCAN. So let's add a PSCAN to this project. Again, you come over here to the menus or the file directory list and add parameter scan. And that creates a new file. And right now it's pretty empty. And now you can go into your model. You can do in XML or the Python, actually probably any file. Let's go back to this. What we're going to do is we are going to do a scan of a couple of these condensing values. So let's do, just because I don't want this to take too long to simulate, this is medium to condensing. And our condensing cell is supposed to be in the middle. We really want the medium and condensing cells to stay away from each other. So what you do is you select it, select the value, and say add to scan. You get a window and it wants an identifier, just a label for it. And I like, for J values, I like to use what they two are. So J underscore medium to condensing. You want to give it a minimum and maximum value. And we'll kind of slam it back and forth. Let's do something even worse than that, and 20. And 3 steps. The distribution is linear. You have some other options. And you also have the option whether it's an int or a float or a string. In this case, float's fine. If you click generate, it'll tell you the values that it generated. So you can double check. Particular number of steps is kind of a vague concept. This is actually 2 steps. It gives 3 values. But in any case, you hit on generate and see the values it generates. Make sure it's doing what you expect it to do. So it's going to do 3, 11.5, and 20. And tell it okay. You'll often get this little message about program file has changed and you should reload it. You always say yes, because what has changed is this parameters.json file. So here's our parameter name, the original value, which is useful for undoing things. And now I'm not sure if I need the quotes. Probably don't. And my list of values. I'll make sure I save. Now I'm going to switch back real quick. We fork the project. Right click over here on the left, add parameter scan. Double click to open so you can see it. Select a value, right click, add to scan. Use the little dialog box to give it a name and the range of values. I can continue, right click on another number here, add it to scan and scan that parameter as well. I can do the same thing in the Python. The tricky part in Python is what you want to click on is the number, not the name. But if I want to scan cell target volume, I highlight the 25 and say add that to the scan, not the variable name. So that all ends up in our file, in our JSON file. If we look back at our original code, it's replaced the value that was there with this. So that's the tag that the PSCAN uses to figure out what values to change. You can put that value anywhere you want. So I'll put it down there. And now these 2 parameters would sweep together. That's not terribly useful. You might want to do it every once in a while. More useful place where you'd want to recognize that tag and reuse it is out here in our output. We can do this. So there's the tag again. Oh, actually, I should make sure. So there's a tag. So when the PSCAN runs, it'll pick a value from its list for JMC. It'll put that value in the XML. It'll also put it in all the other files. So it'll also put it here in my little results printing routine. And it'll print, so I can print that J value along with the result of my simulation. So as I say, you work your way through, you add as many things as you want to the parameter scan. You can edit this file directly, the JSON file, if you want to. It's tricky. You have to, there's some caveats. There's no final comma in a list. But if I said it for debugging, I just want to get rid of this. Now that parameter is only going to have 1 value. That can be handy for debugging because parameter scans can be very slow to run if you got a lot of parameters that you're doing. Okay, so I have we're just going to scan the 1 parameter. If you look in your CC3D file, you've now got a new file listed there along with your steppables file. You've got your parameter scan JSON parameters. Now we're going to do a run. We're going to see fingers crossed. So everything is set up for a parameter scan. I've saved it. I can do it directly from Twedit. Not necessarily the greatest way in the world to do it because your parameter scan can take 5 days, but you can at least test things directly in Player. Now that we have a parameter scan, though, we get a different dialog. And it's going to ask us what the simulation we're doing, and it autofills it, so that's correct. Where it wants to write the output, and the default is into the workspace directory. Whether or not we want to save snapshots and screenshots. I don't think we want snapshots. We'll do some screenshots. A check mark for using the GUI. If I check this, it'll open up the GUI and show us every painful step of it running. The CC install drawer we don't actually need. This is a handy button, display the command line. So there's the command if you want to run command line. And there's reasons for doing that. In particular, it lets you exit Twedit and have the thing running off somewhere in the command line. You can also repeatedly issue this command in a command window. So in a terminal, put that over there. I hope copy still works in this command thing. Wrong command window. So I paste it in, and when I hit return, it'll run. And I can actually paste the command in 3 or 4 times in a row. Paste it in, carriage return, paste it in, carriage return, paste it in, carriage return. PSCAN will take the first one that runs, will do the first set of parameters. The next one that runs will know that the other one is running, and will go on and start the next set of parameters. The third one you set will know the first 2 are running and go on to the third set of parameters. On your home machine, that might not be terribly useful because you're probably going to saturate your CPU. But on a cluster, it's very useful. You can have 25 copies of the PSCAN running all at once, each on a different node or on a different box or whatever, and have them all going at the same time. We are going to run locally. Like I say, fingers crossed. So here's my window. I think I have it set for either 1500 or 2000 Monte Carlo. So it just finished. Here's the command window. So I started up another simulation. We'll wait, we'll let this one finish. There it finished. And then I started up the third one. We'll let that keep chewing. Here is my, oh, that's not the right folder. Here is my workspace folder. This is the most recent one here. I open that. Uh-oh, where'd my files go? There we go. Yeah. So it creates, as always, CompuCell created a folder with the base name being the simulation name, cell sorting base, adds on parameter scan to the end of it. If you go into that folder, you get a folder for every one of your iterations. So here's iteration 0, cell sorting base. I told you to save screenshots, so I've got all my screenshots. So every one of my scan iterations created one of these folders. Now we'll find out if my trick of trying to save results worked correctly. And you have to give me a moment, I'll have to go find that window. So in my Python code, and I had said earlier, I opened a result file, and it's in my top level main directory. So cell sorting based simulation, inside there is my simulations folder. And I was writing to, with a hard coded path, writing to this results file. See what's in it. Here's the results file. Those 2 lines are dummies from when I was testing the code. I'm appending to this file. So every time I run this file, this project, it'll generate another line of another line in this folder, another line in this file. Here's the cell sort simulation. So my medium to condensing J value 3, 11.5, 20. And then the contact area, the thing I was calculating. And I wonder if that number there is right. That's a suspicious value. It shouldn't be that low. I may have a bug somewhere. But anyway, the goal was just to work through running the cell sort, excuse me, running the parameter scan. So let's go back to our slides. Let's get some of these windows out of here. So once we have it all built up, we right click on our project, open in player. Since it knows it's a PSCAN, we get this PSCAN window. Usually the defaults are all pretty good. You might want to make a decision about saving snapshots and screenshots and whether or not you're going to use the GUI. It'll be faster without the GUI. Eventually, if you want, you can display the command line and copy and paste it in a command window, or you can go ahead and run it directly from here. This command is kind of disassembled here on this slide. I've got continuation characters, which are different on different platforms, which you can go through and actually see what all the parameters are. If you need to, you could write this command from scratch. So we're pointing at the parameter scan bat file, which is down in the compcell directory somewhere. And then the input file, which is our simulation directory, or output directory, the installation directory, which I'm not sure is actually needed. A screenshot frequency, you'd also would have snapshot frequency if you want to do that. And like I say, we can submit that multiple times, this command multiple times, and have them all running at the same time. Let's see, 542. I know we've gone through this. So in your workspace, you're going to get a folder for the parameter scan itself. Inside that, you'll have the output for every single one of your iterations, up to however many iterations you had done. You can stop it. If you're running it directly from Twedit, you can just close Twedit and that'll stop. Other than that, you probably have to go into your systems console and in order to kill a parameter scan that's running and kill the Pythons that are running. There are ways in Linux you can use no-hup so that you can no-hup parameter scan command. You can close the window out, log off, and it'll keep going. If your parameter scan crashes or you stop it, if you just reissue the command, the scan will start up where it was, where it had left off. You might lose the simulation that crashed, though. The tricky part is if you ever want to redo the parameter scan from the beginning, you need to go and delete that workspace directory. So you need to come back to our workspace. If I run another parameter scan with this file still existing, the PSCAN code will come back immediately and say the scan is done because it sees this file and it sees inside of the file that everything is there. So if you want to run it again, you can either delete this file, which is an easy thing to do, or you can just rename it. Since the parameter scan code is looking for a particular file name and it's no longer a folder name. The folder name's been changed, so I can run it again. I'd get a new folder, new parameter scan folder, etc. But normally you would just nuke this file and start from scratch if you ran into any problems. I had mentioned this earlier. You can edit this file if you figure out you put way too many parameters in and you can't get through your debugging of writing all the results to one output file and things like that, you can always edit the file and make it much smaller. Save a copy of the original PSCAN file somewhere, edit, make it small. Now you can run your PSCAN, and if you set all your values to a single value, so this particular version will run exactly one simulation. There's only one value for each of the parameters. Super handy for debugging and making sure everything is working correctly. So this is how you get it to run fast. So before you do your PSCAN, make sure you're generating output that you need. You might be generating a table. If you're doing multiple parameters, you probably want to generate a table that lists every parameter that's being changed, the value for that particular simulation. And then whatever your output metrics are. For cell sorting, you might do condensing to non-condensing surface area, condensing to medium surface area. There might be several different parameter or metrics that you're going to output into your log file. You can then use that log file and open it up in your favorite statistical program and start doing analyses about how the parameters are affecting your outcomes. We've already done this. The demo already had writing to the file. If I run my PSCAN again, my little log file will just get a new version in it. So this file will just get some more lines added into it. You can get fancy and make it comma or tab separated, so it's easier to read this file into, say, Excel or something like that. You can put column headers in. However, every run is likely to put a row of column headers in there. One other thing that's really easy to do with the parameter scan is sometimes really helpful. Let me go back to my Python or to my steppable. So that all worked great. As you probably noticed, every time you run a copper cell simulation, you don't get the same results. So one thing that you can do is something like iteration equals 1. And then just select just the value, add to scan, call it iter. And it says it's going to run to 10 steps, linear, and making it, not that it matters a lot, generate, just to make sure 1, 2, 3, 4, 5, 6, 7, 8. Yep. What I want. Tell it yes, it's okay to reload. Now I have my 3-bit J, this one J value that had 3 values that I was scanning. But now I've got this variable called iter. And now what it'll do is it'll run this value 10 times, and then it'll run this value 10 times, and it'll run this value 10 times. And in our log file, we'll get a line for each one of those. And so we can get a little bit fancier and go to our log file. So in addition to writing our JMC value, we can do and I'm going to go up and just steal it from up here. Just to be sure, just in case, and make sure I got did that on the wrong line. That's just printing to the command console. Let's see, making any typos there? I don't think so. This iter could actually just be this. Let's see, I renamed my parameter scan file. Save this one. So it should let me do another scan. Save, yes. Open in player. I get this window. We'll save some space and not save all our snapshots. And we won't use the GUI. We'll run it. Here's the command window. Yeah, I wonder if I still have my log file in do. Here's the log file. I probably shouldn't have done 10 iterations, or I should have done 2 iterations. This is just a demo. Oh, I got a bug. So we got my parameter scan. And so this is why when I said earlier on, make sure everything in your code works before you set up the parameter scan, because it can get really, really tedious to try and fix trivial things like Python typos. Now, since I had the scan running, need to get rid of that. So this will redo. And as I said, let's just do 2. And the last comma is not needed, which is just a JSON foible. No GUI, no screenshots.
Excuse me, I have maybe a silly question.
Sure.
Yeah, this version that is written there in the JSON file and in the Python file, maybe it's just does it really matter what number is written there, or it's like it always runs with your CompuCell version, right?
You mean in the window that lets you set the simulation up?
Yes, also, yeah.
The PSCAN window, the dialog where it says you turn on and off the GUI. Yeah, everything in that window should be populated automatically by Twedit and PSCAN. You shouldn't have to change the paths or anything like that. The only thing you really want to be changed is whether or not you want to save screenshots and whether or not you want the GUI running or not.
No, I say bring up your parameters.py window, please. Yeah, the version, yes, on the top, version 4.0.0. It's just doesn't change anything, right?
No, well, I don't know. I think the PSCAN code has gone through a couple of iterations, and there are some older versions that only work with older versions of CompuCell. And so Maciek had put in that we're actually going to track the version number. I suspect right now you could have any number up there. And I suspect this number is outdated. It probably should be 4.6.0 since PSCAN probably has been, a PSCAN comes with every version of CompuCell.
Oh, okay.
But there may be a check. If I put 3.00 and it may well throw an error and say this is an old PSCAN file. I can't use it anymore.
Oh, okay.
But this was auto-generated when I said, add PSCAN. So you don't have to worry about too much. It should be correct. So this simulation's been crunking along and it looks like it finished. Yep, says parameter scan complete. And I come over here to my log file. And now, so I have 3 iterations with I did 2 iterations of each. So here's J value 3.0, the first iteration and the second iteration. So if I got replicates for each one of these. Looks like probably in the Python, what I should do is actually in this, I should swap the order of this. All this is going to do is in my output file, I'll have all the iterations, a parameter set together. So instead of scanning this value first and then doing the iteration, I'll do the iteration first and then the value. And I'm a little wondering why this last value keeps coming up as 1. Must be some bug somewhere. Okay, so that's parameter scanning. Like I say, super handy for scanning, exploring parameter values. Super handy when you say, my model gives different results every run. Let's do 3 runs or 5 runs or whatever, and generate averages. It can be used for doing sensitivity. It's not perfect for sensitivity. It'll do everything you want. Unfortunately, it'll do things that you don't necessarily want. In a sensitivity, what you would typically do is you change each parameter by some amount that's enough to make CompuCell behave differently. If you look at the literature and sensitivity analysis, they say change the value by 0.1%. In CompuCell, changing something by 0.1% won't make any difference at all. So you might have to change it by a lot more. So you might do 4. Now this is the start of a sensitivity analysis. It's interesting. There is a decimal point there. So I get 2 runs, one with the J value of 3, one with the J value of 4. The sensitivity of the model of the model to the parameter is the change in the parameter divided by the change in the model output. No, upside down. Change in the model output. So in our case, it would be this value. How much does this value change per unit change in this value? Usually you normalize those values, but you don't have to. So what we do is, you don't want to edit it that way. What we could do, if we wanted to compare sensitivities of different J values, this is M to N. So now it's also going to do a scan of these 2 values for M and N. There will be a scan for undid my changes. It'll do 3 and 5, and then it'll do 5 and 5, and then it'll do 5 and 6, and we'll do 2 iterations for each. But this value, when it's frozen, when it's the base value, these 2 values are the sensitivity for this value. When you do these 2 runs, if you find the simulation that always had 3, that's the sensitivity for this value. So you'd have all the information you need in this table to calculate sensitivities. There would be some simulations you don't need, because in a sensitivity, you usually only change 1 value at a time. And the parameter scan is going to do that, but then it's also going to change 2 values at a time, and 3 values, 4 values at a time. So there'll be extra simulations. So this can be done, it can be used for parameter scan or sensitivity analysis. It's not optimal. Sensitivity analysis might be a place where you want to run, use the CompuCell API, and take care of selecting your values in the API and doing the sensitivity calculations and stuff like that. in Python calling CompuCell via the API. It can be done here, just not necessarily the greatest way to do it, most logical way. Okay, I think we're right at 6 o'clock. You want to do an exercise. So in the shared folder is that cell sorting demonstration, nice simple file. You can try adding a parameter file to it. Remember, you right click over in the left hand file hierarchy and say add file and tell it it's a Python and add it in. Add in some things, some text into it, define a parameter, and then import the parameter file into your Python and try to use one of those parameters. So make sure you do the questionnaire. I'm going to stop there. I'll leave this up if someone wants to give it a shot. You can also try adding a parameter scan once you get your parameter file defined, which is separate from parameter scan. But then go ahead and try to add a parameter scan on top of that. Let's see. Yeah, the comments from James is right. You have to take into account stochasticity. So you do want to do multiple runs if you're going to do sensitivity analysis. Sensitivity analysis is an entire research project in and of itself, though, because there's a lot of complexity in doing sensitivity analysis. Usually what I've done in the past is called single point sensitivity analysis. When you get your model to do what you want it to do, so for in the cell sorting simulation, you get a set of parameters that sorts well. You then do a sensitivity around that point. Your reference and base set of parameters is that set of parameters that worked well. There's also global sensitivity analysis, and in that case, you don't constrain yourself to stay near a good solution. But that is much more complicated and usually requires many, many more runs and gives you sensitivity at other solution sets. Again, that's probably a situation where it would be better to use Python running an API and to run CompuCell so that you have better control of exactly how you set up your parameters and how you analyze your results. A Jupyter notebook is probably not the way to go, since it's likely your parameter scan is going to take many hours, and you probably don't want to sit there and watch your Jupyter notebook go for many hours. I'm just checking some of the notes. This is the chat. Yes, so as Julio had asked, yes, it runs the exhaustive exhaustive combinations of all of your parameters, which is why you have to be careful about doing, let's do 5 parameters with 5 values each. Well, that's 5 to the 5th simulations. That's a lot of simulations.
Maybe a good question would be how to control or maybe know what's the random seed that it's using or controlling it all.
Okay. That's a can of worms that we've been fighting for a long time. This is a Python only simulator. Let me get a regular, more standard. Can't believe I don't have a handy XML project. Now, I don't remember where it's at. I'll have to, when in doubt, you can't remember how to do something. Remember that all these little helpers can give you all kinds of handy hints. So this is an XML file. So this is CompuCell markup language. I don't remember if it's in plugins. No, it's not in plugins. I'm not sure if it's in pots or in metadata. There it is. This is the command I was looking for. So I'm going to copy that and I'm going to undo all my other changes and just stick that in there. Okay, I can assign a random seed. And every run with that random seed should generate the same output. However, we are finding some problems with getting that to work correctly. And the most common cause of the problem is if in your Python steppable do import random. And somewhere in your code, you're using a random number generator. You're flipping a coin to see if you should kill Excel or not.
Oh, I see. Yeah,
This
two random number node generators.
Yep, and they're not using the same seed. And you would think that this would work. I don't remember the exact syntax. And you can put any number in. And it doesn't have to match the other number, but it just has to be some specified number. And now your simulations supposedly are all going to be the same. The problem is you import NumPy, import, now it's the graphics package. .graphviz or matplotlib or something like. Start importing other packages and you never quite know if they're importing the random number generator themselves. And so we've been having some trouble getting this to work correctly. Trying to think if there's an easy way of finding. What's the anybody know offhand what the syntax is for the random modules? Yeah, it is just seed. So that's correct. We got about one set over here. Doesn't really matter a whole lot what number you pick. But we'll try. We'll see if it works. What we'll do is we'll just run the simulation a few steps. Run 11 steps. And that's definitely a random choice. Just want to scrape that, what that looks like. And run it again. Now the question is, these two images match? Yep, they do. I'm looking in particular at this one pixel, these pixels down here.
Okay. So yeah, so maybe maybe you fix them all the seeds.
Maybe,
yeah, seed for
maybe we
for
fixed it,
yeah, okay.
or maybe I just have a simple enough simulation. I haven't imported a bunch of other modules that are going to confuse, that have their own random number generator. But this seems to work. Compare it this way. And look at the top. Yep, it matches. So you can do it. It's a good point. There is a really good reason for using a random number generator, and that is in debugging. Sometimes you'll get a simulation that is crashing, and the problem is it's not crashing in a consistent place. One time it's 500 MCS, another time it's 1100 MCS when it crashes. You can set the random number seed so that it crashes at the same time every time, and then go into your code and say, well, it's crashing somewhere around step 5,000. So at step 4,000, I'm going to put in a whole bunch of print statements and start printing stuff out, see if I can figure out where the bug is. So that's super useful when you've got a deep bug that you can't find, and make the simulation do the exact same thing every time, and you can kind of winnow in on where the problem might be because you know what code step it's going to crash at. Oh, and James made a good point that multi-threading may confuse the random number generator. That's right. I think every sub window is going to get another instance of the random number generator. We could test that real quick. I still have the codes running. So I have one processor. I'm going to run 11 steps. So I had thrown away my image. I shouldn't have thrown away my image. We don't need the whole thing. Now what we'll do is go, let's do 4 processors. Yeah, I was looking for this command. I couldn't find it. Okay, so we save that. We still have the random number seed defined. Real fast, 11 steps. Now you can see that they don't match. So sure enough, that was one of the bugs we were chasing. The seed works as long as you only use one thread. If you use more than one thread, every thread gets its own random number generator. And that was the bug that Maciek was chasing to see if he could figure out a way to get rid of that problem. So a good take home. Set a random number seed, but then you can only use one CPU, one thread. Yeah, Lorenzo says that each thread creates its own M twister. When we log off here, I think I'll go and make sure that's in the Reddit notes on the random number generator. And James says in the chat, it's not a bug, it's a feature. Okay, is there anything else? We're a few minutes late, I think. Or are we in the discussion section?
Yeah, we're just in Q&A now. We're not too behind. Great. Well, thanks, Jim. Any questions for Jim on anything he presented? I know it was a big chunk of material, but very useful and practical stuff. So any other questions? We'll be here till 6:30-ish for people who want to ask anything or discuss. Question in the chat. Unless you need to replicate exactly, I think it is the way to. Okay, unless you need to replicate exactly, I think it is the way to go. Why keeping a random seed fixed?
Yeah, and yeah, normally you would not set the seed at all. You only set the seed if you're trying to force it to the same thing every time. By default, Python will use one of the techniques for generating a random seed, like setting it to the clock or something like that. So normally you don't want to do random seed.